Good morning to everybody. I am pleased to present you the talk of Professor Stephen Wilson. This is a very condensed bio of his scientific works. Professor Stephen Wilson holds since 1984 chair in mathematics and leads the Continuum Mechanics and Industrial Mathematics Research Group at the University of Strathclyde in Glasgow, in United Kingdom. He's interested in the application of mathematics to a wide range of real-world problems in fluid mechanics, such as thin film flows, evaporating droplets, microfluidics, liquid crystal, confined bubbles, thermoviscosity, and etc., and in many subjects. In his work, we can find an insightful and innovative use of a wide range of mathematical methods, notably asymptotic method, which leads to new insights into a wide range of fluid dynamics problems. Professor Wilson and his collaborators jointly awarded the Institute of Physics, Printing and Graphic Science Group Prize in 2009 for their fundamental study of droplet evaporation. He was, 14 years, the joint editor-in-chief of the Journal of Engineering and Mathematics by Springer Nature, and his fellow of the Institute of Mathematics and its application in the United Kingdom. He will talk in this Congress about the recent developments on the evaporation of sessile droplets, competitive evaporation of multiple droplets, and the evaporation of droplets on non-planar substrates. So we listen you for your talk.
Thank you very much indeed for that very kind and slightly generous introduction. It's a great honor to be here. I want to start by thanking the organizers very much for inviting me. I am genuinely honored to have been asked. And my only regret is that I'm not able to be physically with you in the current circumstances in Argentina. I was very much looking forward to visiting. I think traveling the world to visit new places is one of the great perks of academia, which I usually like to try and do. Unfortunately, that's not been possible in the last as we know. I'm afraid I'm doing this from my house in Glasgow. Of course, this is quite an interesting week to be in Glasgow with COP26 going on a couple of miles or 3 miles away down the road. But I would have liked to have been with you. Unfortunately, that's not possible. So I will do our best in the circumstances, and hopefully I'll have something worthwhile and interesting to say to you that you might think was worth the effort of listening. So yes, thank you very much. And the long title was the one that you said. My short title, which is a little easier to say, is the one at the top of my slide there. And what I'm going to be telling you about today are various mathematical models for evaporating droplets. These droplets are all going to be on a substrate, so not free droplets, but droplets sitting on a solid surface of some kind. And that's why the word sessile was used in the long form of my title. I'm going to talk about several different aspects of the problem. It's a fascinating problem. And the ones mentioned in my title, I'm going to talk about what happens when there's more than one droplet. And I'm going to talk about when the droplet is not sitting on a flat surface, but a more interesting one. And I hope in the time available to be able to cover all of those topics. I'll finish with a slide with some references. And so if you are interested in more details of any of these problems, then luckily, fortunately, just the way the timing has worked out, most of what I'm going to say, essentially all of what I'm going to say in one form or another, is available now as a published paper. And so that information will be out there. So I apologize if I skip some vital detail. I'll try and do my best, and I'll try and get the ideas over, and if you want the details, then they're available. Okay, so I'm at Stephen Wilson. I'm at the University of Strathclyde in Glasgow. There's my email if you want to contact me after the talk, and if you're have nothing better to do with your time, you could always follow me on Twitter. So before I talk at all about the science, I need to talk about the people who did all the work. So people, and that's because it's a problem. The droplets and evaporation of droplets is a problem we've worked on for, well, gosh, getting on for 15 years now in various different forms. It's not the only thing we do, but it's been quite a big part of what we do. And that's been with a series of PhD students and collaborators all of whom have really made vital contributions. And I can genuinely say, without any one of these people, we wouldn't have been able to do all the things that we've done, and some of the things I'll tell you about today. So some of these names you'll hear again, some of them you won't, but I want to mention them all because they've all played a very important part. So just quickly going across from the top left, Gavin Dunn was our first ever PhD student. He had the task of teaching us about droplets in the first place, and I'm eternally grateful to him for all the work he put in. Our second PhD student who kind of took over when Gavin left was Jutta Stauber, and she worked on some fascinating problems, and I'm going to talk a little bit about some of her work. Our third PhD student who worked in this area, Feargus Schofield, he finished a year or two ago, and we're going to talk a little bit about some of the things that he did. And finally, on the top line, our fourth and current PhD student, Hannah May D'Ambrosio. She's very much still with us, working on her thesis now. And the final part of today's talk is going to be part of her PhD work. Now, on the bottom row, I've got my friends and colleagues who I've worked with over the years, and I want to give them all due credit for their vital contributions. So first, on the left, my great friend and colleague, Dr. Brian Duffy. I've worked with Brian on many problems over many years. You could not ask for a better, more patient and cleverer collaborator. You may not have met him. Brian, not a great fan of traveling the world and going to conferences, but if you want someone to do some mathematics to save your life, my money would be on Brian. A great collaborator, and as always, I'm very grateful for his essential, vital, key contribution to this work. Second, my friend and colleague, Dr. David Pritchard. David co-supervised Feargus with me, and he played a crucial role in the work that Feargus did. Two things you need to know about David. One, he's a really bright, up-and-coming applied mathematician, and secondly, he's not as scary as he looks in that picture. Thirdly, my collaborator, colleague and friend, Dr. Alex Wray. Alex joined the University of Strathclyde from Imperial College 2 or 3 years ago. He's been a fantastic addition to the team here, and he brings a whole range of skills, particularly on the numerical side, that we didn't previously had. And a lot of the recent work, a lot of the stuff I'm going to talk about today is joint with him. My long-standing friend and collaborator, Professor now Khellil Sefiane from the University of Edinburgh. He's been an essential collaborator from the outset. He's an experimental scientist and engineer based at the University of Edinburgh, and his common sense and grasp of reality has on numerous occasions stopped us mathematicians getting carried away. And he's been important. He's been very good about pointing us in the direction of the really useful, exciting and interesting new problems. And he's also, as I said, been very crucial in keeping our feet firmly on the ground when we might have wanted to get carried away in some of the mathematical niceties. And finally, but by no means last, Professor Colin Bain from the University of Durham. Colin is a very skilled chemist and has worked on droplets and related problems for many years. And we've recently, with Hannah, had the chance to collaborate with him. And I hope when we talk about that work, you'll realize how useful that was. And the work, he brings an experimental aspect to things that we don't have ourselves at Strathclyde. So all these people are crucial, and some of these names you'll see again. Okay, so droplets, sessile droplets, in other words, droplets on substrates of some kind are of course ubiquitous. They make for very beautiful photographs, and you see them every day. For example, famously, when you spill your tea or your coffee on the desk, if you come back the next day and you haven't wiped up where you spilt, you'll get these fascinating coffee stain patterns left behind. And that is just one of the many fascinating features, and I will talk briefly about that coffee staining problem. The coffee stain, by the way, if you don't know, is this feature whereby instead of getting a uniform deposit of coffee left behind when the liquid is all evaporated, you get this characteristic pattern with the coffee granules around the edge of the drop. And the mechanism by which that occurs and the details of that and all the aspects of the science that reveals is an active, very active area of research. However, an important thing to bear in mind as we do this is that drops generally come in their battalions. They come in many. You very rarely in real life get single droplets. In the lab, yes, people do very careful controlled experiments with single drops or very small numbers of drops. But in real life, and here are some examples of real life, drops, many of them at the same time, And so an important aspect of the problem I'm going to talk about today is what happens when you have more than one drop, and in particular when those drops start to interact with each other. And that's a problem that's had a great deal much less work done on it. Okay, so that's the general introduction. So the talk comes in 4 parts. Hopefully that won't be too, breaking it up won't make it too painful for you. So the first part is just talking about the basic theory for a single droplet. That's probably, for some of you, you may have seen some of that material before, but it serves as a useful introduction to what follows. And I think in itself is still of great interest, I hope. So part 1 is about what happens to the evaporation during the evaporation of a single droplet. Part 2 returns to the question I just mentioned about what happens when there's more than one drop. And I'm going to describe some recent work about what happens when we have more than one drop evaporating in proximity to each other, and that turns out that it means they're competing with each other. Then leads very naturally to the third part, where we're going to talk about what happens if the drops contain a passive particles within them. For example, like those coffee granules, those particles of coffee that I was talking about a moment or two ago. If there are particles that start off in the droplet, where do those particles end up when the fluid is all evaporated? The fluid is gone, but the particles stay behind. That's the classic coffee stain problem that I was just describing to you. And then the question is, what happens? How does that work? What happens to that problem when there's more than one drop? That's also very recent work. And then finally, what happens if the substrate is flat, and what happens when we put the droplet into a well? And I'll explain why we might be interested and try and indicate what happens in those cases. So that's the agenda. I hope I'll be able to cover it all in reasonable detail. If you find yourself drifting off and losing concentration during one part, you can always drop back in again when we get on to the next one. They're all variations on a theme. So let's begin with part 1, and let's talk a little bit about a single droplet. We're going to generally, at least in this talk, going to be talking about small droplets, and so the effect of gravity is not going to be particularly significant. That means the shape of the drop, if it's sufficiently small, is determined by capillary. And so the picture you need to have in your mind is one like I've drawn here, where you have a spherical cap shape of the droplet with the fluid inside the drop, of course. Outside the drop, you have the atmosphere, and the drop evaporating. Of course, what that means is that the fluid is vaporizing, and molecules of the fluid move from the fluid state within the drop, and they move out into the atmosphere as vapor. The arrows on this diagram around the top indicate the flux of vapor, of liquid, from the drop into the atmosphere. That's going to be denoted by J all the way through here, and clearly determining J is absolutely crucial, because once we know what J is doing, we know how the drop evaporates. That's a huge step along the way to understanding how the drop evolves. And evolving can mean various things. Of course, the shape will be changing over the course of time. In particular, the radius of the drop, that's capital R in my diagram here. That's the size, the width of the drop, of the drop on the substrate, and the contact angle. And the contact angle, denoted here by theta, is the angle that the fluid makes with the solid. Many of you will be very familiar with that concept. And as the drop evaporates, we're going to find that R and or theta are going to decrease. And eventually, finally, ultimately, when all the liquid has evaporated, all the fluid will have gone, the drop will have collapsed, the radius will be 0, the contact angle will be 0, and there'll be nothing left, just the dry substrate. The calligraphic R here shows the radius of the equivalent sphere, and that's a useful concept when we're looking at the shape of the drop. Okay, so what's the mathematical problem, and what kind of physics are we trying to represent here? So the evaporation of a drop is a long, complicated story with many different potentially important physical effects. But for today and for most of the work, essentially all the work we've done, and for much of the work that's been done, we're going to focus on the simplest situation, where the evaporation of the drop is driven purely by diffusion of vapor from the drop into the atmosphere. So it's a purely diffusive process, and as you might perhaps expect from diffusion, that means the concentration of vapor in the atmosphere, which we're going to denote by C for concentration, satisfies the Laplace's equation, subject to appropriate boundary conditions. So this, in mathematical terms, is this very, very classical problem. The complication, of course, comes from two sources. The equation is Laplace's equation. The complication comes from the fact that, firstly, the boundary conditions are mixed boundary conditions, so we get different boundary conditions on the drop and on the substrate. And secondly, of course, the shape of the drop is itself evolving, so the domain in which we're solving is evolving. And that means that even though this looks like quite a simple classical problem, and in many ways, of course, it is, solving it in all but the simplest situations is already quite a challenging problem, as we'll see. But progress can be made, and I'll talk about that shortly. So specifically, the boundary conditions are the following. So on the substrate, there's no liquid, and so no evaporation. And so what that means in terms of the concentration is the normal flux of the concentration is 0. So on a flat substrate, dc by dz, the normal derivative of the concentration is 0, a simple no flux boundary condition. Alternatively, on the other hand, on the drop, the simplest physical model is that the vapor saturates the atmosphere just above the drop. And so the appropriate boundary condition is that the concentration of vapor, C, is equal to the saturation value on the droplet. And in the simplest version of the model, that's simply a constant. We'll talk a little bit about other situations later. In the far field, the concentration has to go to an appropriate far field value. If we're talking about evaporation of water, then that would simply be going to the ambient humidity in the atmosphere. That, of course, depends on where you are, and what, where, when, and what time of day, and it'll be different for you guys in Argentina. It's certainly different here today in Glasgow, and experiment in Edinburgh varies slightly from day to day. So that's an experimentally determined quantity. As far as we're concerned, mathematically, it's a known constant. If we're working evaporation of something else, say, for example, acetone or some other more volatile liquid like that, hopefully there isn't too much acetone just lying around in the atmosphere, and so the atmospheric concentration there would be 0. But again, it's just a constant, so it all fits within the same model. Okay, so that's the mathematical problem. We've already talked a little bit about the shape of the drop. We're going to assume it's small, and so it has this quasi-static profile, and the equation there at the lower half of the slide is simply the expression for a sphere written in the appropriate way in terms of R and R. So capital R is the contact line radius, and theta is the contact angle. Of course, once we have the shape, we can just integrate it to get the volume, and you can write that in terms of those quantities. So that's just a piece of simple geometry. Crucially, and what connects the two problems together, is that the volume of the drop will change the evaporation. So to calculate the rate at which the drop volume changes, dV by dt, we need to integrate the flux over the surface area. So the integral of J ds, the integral of J over the surface of the drop, that quantifies the amount of material that's leaving the drop, and so therefore that tells us the rate the volume is changing. There's a minus sign there, and of course that minus sign is because fluid is always, molecules are always leaving the drop, and so the volume will always be decreasing. You could imagine a kind of corresponding problem to do with condensation. It turns out that's actually quite a more complicated situation, and it's not just simply a matter of reversing the sign there, but that's another story, and I don't have time to tell you about that today. In fact, I understand much less about that problem, but it's another fascinating aspect of the same topic. Okay, so that's a classical problem. So it is possible to write down an exact solution to that problem. It is a classical solution. It was originally written down not in the context of drop evaporation, but in the context of electrostatics, because of course there's a completely equivalent problem in electrostatics about the field around a charged sphere. So this problem was already solved. The form of it is not particularly nice, but it is possible to write it down. I'm not going to write the whole thing down for you, but it is known and it can be used. And in particular, if you use that solution, you can evaluate what the flux is. So what I show here on this picture is the flux indicated with the arrows for a drop with a low contact angle, top left, all the way through to a drop with a very high, in fact, a 180-degree contact angle on the bottom right. These are plots of an exact solution, but they show you some rather interesting properties. They show you that for small contact angles, and in fact that means contact angles up to 90 degrees, the flux is largest at the contact line, at the edge of the drop. Those large arrows show you that. In fact, mathematically it's singular, so it goes to infinity, but luckily for us, it's integral, and that integral of J term is finite, and we can use that to calculate the evolution, and I'll show you examples of that shortly. For a drop with 90-degree contact angle, it's just everything is symmetric, and so the flux is uniform. And as we go to large contact angles, the picture's kind of flipped up the other way. The flux is actually now 0 at the contact line, and it's largest in the middle of the drop, and that's what those arrows show. I should say, if it wasn't clear, the length of the arrow indicates the relative size of the flux in all of those pictures. So this is the picture you should bear in mind as you think about the evaporation of a single drop, as the contact angle goes from being small up to 180 degrees. Okay, so however, there's one big question we haven't yet talked about, and there's one big piece of the puzzle that's still missing. We can work out how the volume's changing, but that doesn't in general tell us how the radius and the contact angle are changing. Essentially what we've got is we've got one equation for two unknowns. We've got the equation for the volume, which is an equation for a combination of r and theta, but that's no good to us. Well, I mean, that is excuse me, that's very helpful, but of course it doesn't individually tell us what r and theta are. R and theta are two unknown functions. We've only got one equation for them. So in order to work out how the drop itself evolves, how r and theta individually evolve, we're going to need to make an additional assumption. So in principle, that would involve doing some more detailed mathematical modeling, but what we're going to do here is just proceed more pragmatically and make some assumptions about the various different modes in which a drop can evaporate. And this is very much inspired by what's observed in the experiments. So there are two what are called extreme modes, the two simplest possible situations, easiest to analyze, useful, and actually also really genuinely seen in physical experiment as well. The first is the constant radius mode, and as you might guess from the name, that means that's a situation where the radius of the drop r is constant, is fixed, the contact line is pinned in place on the substrate, and therefore as the drop evaporates, what happens is the drop collapses downwards, the contact angle decreases, but the radius stays the same. And that typically, that is typically what indeed happens on normal or rough substrates. The contact line is reluctant to move, and you get this constant radius pinned mode. The opposite, the other extreme, is where the radius decreases, but the angle is fixed. And that, of course, you would imagine, of course, is called the constant angle mode. That's observed less commonly in practice, but certainly is observed in practice. It occurs on a smooth substrate, and people have done experiments on smooth substrate showing that. And it also occurs in the third mode, which is what's called, I'm going to call here a stick slide mode. And this, I would say, if you wanted a typical example of what really happens in a normal experiment, what normally happens if you were to do a typical experiment is you start off in the stick, in the constant radius mode where the contact line is fixed, as shows on the left-hand side of this picture. But what normally happens is you get down to a certain contact angle, and at that point, the contact line then starts to move inwards. And so what you do is you transition from a constant radius mode to a constant angle mode. And so this typical mixed mode, stick in the first phase, slide in the second phase, is what's regularly observed, commonly observed in experiments. And it's the third mode we're going to examine theoretically. Of course, this is not a complete set, and the picture isn't always as clean cut as this in real life. There are also situations where r and theta can vary simultaneously. There's one other mode I want to mention to you, though, and it's the stick jump mode. And again, this is observed typically on rougher substrates. What happens there is the contact line does move, but it does it in discrete jumps. So the contact line is pinned for a while, and then there's a rapid jump where it jumps to a new, smaller contact radius, and you get a series of these jumps. And so that's why on the left-hand side of this picture, and these are experimental measurements from the group in Edinburgh, you get a series of steps as the radius steps down as the droplet jumps in. At each jump, the drop rearranges itself, and so as the radius jumps in, the contact angle has to jump up to conserve volume, and so you get this kind of sawtooth pattern in the contact angle. These are radius on the left and contact angle on the right, plotted as functions of time. This stick jump mode can also be analyzed, and I'll show you a few results for that a bit later. Okay, so we can put all this together. So we can take the solution for the evaporation, we can use that to calculate the flux, and then putting that into the equation for the for the evolution of the volume, we can then calculate how the different quantities R and theta evolve in the different modes. Now, there's quite a lot going on this slide, so apologies for that. So what I've tried to do on the slide is perhaps quite a lot of different results. So these are results for different modes. I've scaled, the droplets will live for different times in the different modes, and so I've scaled that out to try and fit things a bit more easily onto the same picture. What this shows you is how the drop behaves. On the left-hand side, it's how the contact angle evolves. On the right-hand side, it's how the radius evolves, a scaled value of the radius, and the different sets of curves correspond to different initial contact angles. So we have situations where, for example, on the top left, where the angle stays very close to its initial value for a long time and then only sort of collapses down to zero right at the end. On the sort of bottom right, you've got situations where the radius stays fairly close to its initial value before it collapses. So all of this can be calculated from the basic model that I've described to you. And in particular, from this, you can calculate how long the drops are going to live for. And of course, by how long they live for, I simply mean how long it takes for either the radius or the contact angle to go to zero. Sorry, this picture is the corresponding evolution of the volume. It's a little bit less interesting because, of course, in all situations the volume decreases, but in each of those different situations the details of it are a little bit different. But what this does show you quite nicely is that, of course, in the different situations, the time the droplet lives for, the time it takes the volume to go down to zero is different. So let's talk a bit more about lifetimes. So I told you I'd scaled out some key quantities there, and indeed this is the scaling I'd used. So what I did was I scaled out some dimensional parameters, but I also scaled out the initial volume, which makes things a little bit easier to see. So basically, it looks a bit complicated, but it's simply a suitable reference timescale for the plotting. Taking the equation and integrating it up, you can work out the evolution, and hence you can work out the lifetime, and you can actually get some for the three different modes. The first three modes I talked to you about, I've done that here. So here is the constant radius mode. This is TCR is the lifetime of that mode, and it's the expression here. It involves an integral of a function g, which I may show you on the next slide. It's a known function of theta. It's slightly complicated, but it's a known function of theta. So this is something you can work out just by doing the integration. The constant angle mode, very similar. Actually, there's an integration there, but it's trivial, and so you just get an explicit expression without it's easier, if anything. And again, it involves this function g. And finally, in the stick slide mode, I mean, that's a combination of the previous two, so it's perhaps not a great surprise that the answer looks a bit like a combination of the previous two. As I say, this function g is a known function. It's a little bit messy, but it's something we know and have an explicit formula for. The theta star, I should point out here, that's the depinning angle. That's the angle at which we get this switch from the pin mode to the sliding mode. And so in practice, in experiment, that will be something you determine experimentally. And when you do that, then here lifetime. So they're slightly busy, these slides, but I want to spend a minute or two on them because I think they're quite interesting. So let me just explain what we've got here. So what I've got here is on the vertical axis, I've got the lifetime of the drop. And on the horizontal axis, I've got the initial angle going from 0 to pi. And there are three sets of curves. So the solid curves are the lifetimes of the drops in the extreme modes. So the heavy curves, the heavy curve, the solid curve at the bottom is the lifetime of the drop in the constant radius mode. You can see that's those go to zero when theta naught goes to zero, and then increases to a maximum quite close to pi, and then decreases very slightly. The dashed heavy curve is the corresponding lifetime of a drop in the constant angle mode. What you can see from the picture is that's got a kind of similar shape, not the same, but it's sort of similar. It peaks a little bit earlier, but in particular, the lifetime of the drop in the constant angle mode is almost always bigger than that of the same drop in the constant radius mode. In other words, the dashed curve is above the solid curve, at least round about 140 degrees, where those curves do cross over. And if we zoom in, and the right-hand picture shows the zooming in, if you zoom in, you can see that near a critical value, between the critical value and 180 degrees, there is a small region of the parameter space where that picture's flipped up the other way, and actually the constant angle mode lives for a shorter time than the constant radius mode. I think that surprised people when it was first pointed out, because people's intuition about this problem is all based on what happens at small contact angles, and obviously what that's happening there is a phenomena at large contact angles. The set of thinner curves there correspond to the lifetimes of the stick slide mode, different curves for different values of the parameter theta star. So in one extreme we get the constant radius mode, in the other extreme we get the constant angle mode, and you can see that for intermediate values we can fill in the gap in between. But again, this was also, I think, surprising when people first realized this. If you look on the right, you can see there's a region of parameter space, in fact anywhere above theta is 90 degrees, where the thin curves are above both of the heavy curves. In other words, put in words, the lifetime of a drop in a mixed mode lives longer than it would do in either of the extreme modes. And again, when that was first pointed out, people were a little bit surprised about that, because everyone's intuition was based on the fact that the mixed mode, because it was a combination of the extreme modes, would always be in between, but it isn't. And again, it's a large contact angle phenomena. And so here we've got exactly quantifying that and showing that actually a droplet in this mixed mode can live longer than it would in either of the extreme modes. So there's quite a lot of detail here, and all of it comes from the analysis of that relatively simple mathematical model. We can do the same for other parameter values, and you get similar kind of story. There's quite a lot of information there, so it was quite helpful, I think, to put this together into a kind of phase diagram. And so what we did here was we plotted the initial angle against the retreating angle, in other words, the angle at which we get the switch between the modes. And when you extract the information about that from the previous pictures, you get a parameter plane here that has these 6 regions, and the 6 different regions correspond to a different ordering of the time scales. For example, in region 1, the constant radius mode is shorter, has a shorter lifetime than the constant angle mode, and the mixed mode, its lifetime sits in between the two. That's the kind of what you'd expect. That's what people were anticipating, and so region 1 is sort of where people were comfortable. But you can see, and as I showed you from the pictures on the previous couple of slides, that's not always the case, and so you get these other regions of behavior. So I think mapping out the full parameter space here was something that people hadn't done before. I've got a couple of quick asides, details. So I said to you that in the simplest model, the saturation concentration was a constant, and that's true. And that means the thermal problem, the evaporative cooling of the drop, doesn't affect the thermal problem doesn't affect the evaporative problem, and so the thermal properties just don't play any role. However, that's not always true, and in general the saturation concentration will depend on temperature, and in that case the thermal and the evaporative problems are coupled, and that means that the thermal properties of the substrate can now play a role, and indeed they can play quite a strong role. And so one of the things that Gavin Dunn did in his early work was he quantified all of that using the model. And what's shown on the slide here is the evaporation rate for 3 different liquids on 4 different substrates. So the ballpark, the big message is acetone evaporates faster than methanol and faster than water. Well, no big surprise there. We knew that anyway. But if you look at each one of those pictures in isolation, you can see that the effect of the different substrates can be quite significant, certainly for acetone and methanol. And so what the message there is that the more insulated substrate, evaporation is big, and so there's quite a strong influence, and I'll show you another picture of that now. So more recently Feargus Schofield revisited that and worked out a lot more of the details, and he showed how the fact that you get cooling of the substrate means you get less cooling of the drop, and therefore you get less evaporation, and that slows everything down. So on the more insulating substrate you get slower evaporation. Okay, and again, there's more details to that, but essentially what's going on there is a coupling between the thermal and the evaporative problems. And of course, that has a consequence on the lifetime. So if we now, for example, look at the lifetime of the constant radius mode, the solid curve there is the one you've seen before on my previous graphs, but the symbols now show the influence of including the thermal properties of the substrate. And you can see, obviously, different substrates have different effects, but all of them are making the drop live longer. In other words, all of them are slowing the evaporation. And that can be quite significant. If you look at the right-hand end of the graph, there's an increase in the lifetime of getting on for 60–70%. And so in practice, it can make quite a big difference about how long these drops live for. And of course, that has other consequences. In particular, if you're thinking about this in a a heat transfer context, that can have big consequences for the cooling properties that you're going to get. I should say, spraying drops onto a substrate is a classical way of cooling it, and then what happens is as the drops evaporate, they take energy away and cool the substrate. And of course, the properties of the substrate are going to play a role in that. Same thing for the constant angle mode. Qualitatively much the same thing, but of course the details are a little bit different. Okay, so that was part one. So if you get nothing else from this talk, hopefully you've learned a little bit about the evaporation of a single droplet. The remaining three parts are basically taking that basic model and extending them in a couple of different ways, and hopefully that will be of interest to you. So let's talk first about what happens when there's not just one. In particular, let's talk about what happens when there are two or more. So a single drop evaporating into the atmosphere is a problem we've talked about, and of course, because the drop's sitting there on its own with nothing else going on, the solution, the drop, and the evaporation, everything about it is axisymmetric, which is great, and it makes for the mathematics quite much a lot easier to analyze and understand. As soon as you have more than one drop evaporating into the same atmosphere, that's going to change. You can imagine immediately how that's going to work, because the vapor evaporating from one drop is each one drop will feel the effect of the vapor evaporating from the other drop. Put another way, the drops, if you like, are kind of fighting for space. They're both drops, if you're thinking of two, but it works for any number of drops. They're trying to evaporate into the atmosphere, and if the atmosphere is already partially filled with vapor from the other drops, then of course that means there's less space, if you like, for the drop, for that drop to evaporate into, and so the drops are competing for space in the atmosphere. A crowded room, trying to make your way through a crowded room. If there's already a lot of people in the room, it's much harder to make your way through it, and that's essentially what's going on here. And that's why I refer to it as competitive evaporation, and the word that's often used in the literature for this is the effect of shielding, and what's happening there is one drop is sort of shielding the other drops from the atmosphere. So what's clear from that explanation, and certainly true from the mathematical models we've got, is that as soon as you put more than one drop together in competition with each other, they're going to have the effect of slowing the evaporation of their neighbors. So two drops are going to evaporate more slowly than either one of those drops would do on its own. So what we wanted to do here was we wanted to analyze that situation, and of course the complication is that it gets much harder to solve the evaporative problem. In particular, the exact solution that we had access to last time doesn't apply anymore, and I mean in itself for a single drop it was already complicated, but for multiple drops it essentially becomes impossible to do anything exactly, and so we have to resort to some other methods. So, as I said, there's been relatively little work compared to the single drop case on multiple drops, though there have been papers with some important contributions. And what we're going to do here is look at arbitrary configurations, and we're going to make one crucial simplification, and we're going to make the simplification that the drops are thin. Okay, so that means the contact angles are small. It doesn't have to be tiny, but it certainly has to be less than 90 degrees. But in practice, getting up towards 90 degrees, the theory still seems to work rather well, as I shall show you. So the setup is a kind of a general one. We're looking down on the substrate, so these are the footprints of two of the drops. And the problem is exactly the one I already described to you. So it's diffusion of vapor in the atmosphere. It's the same problem as before. It only looks a little bit different because I've non-dimensionalized the problem to remove the dimensional parameters. But physically, it's exactly the same problem as before. The complication isn't in the problem, or it's in the boundary. It's in the geometry, and hence in the boundary conditions. The problem I'm not able to solve, but people have thought about that problem in other contexts, and there's a paper from 1985 by Fabricant where a clever series of integral transformations, he transformed that problem. Well, he didn't solve the problem, but what he did is he rewrote it, and he rewrote it in the form that's on this slide. Now, it looks rather complicated, but really what we've got there is a relationship between the fluxes. So it's not a solution to the problem, but it's a very helpful, crucially, importantly, a very helpful rewriting of it in terms of the fluxes. And I should just say that that prefactor J naught, the expression there on the slide involving the square root of AK squared minus rho squared, and rho is just the coordinate measured relative to one of the drops. That expression is the flux from one single drop. It's a kind of classical formula that we'll see popping up again in a couple of contexts. So that term in the square brackets, the 1 minus, or the complicated equation, the 1 without the big complicated term there, you just have a single drop evaporating in isolation. The minus and the right of the minus, that's the mathematical expression for the shielding. That's the fact that the effect of the other drops is to slow the evaporation from the first drop. And of course, it works for all the drops. All of the drops affect all of their neighbors. Okay, so of course the local flux is great, but what we really want is the total flux, because we want to work out the change in the volume, and so we get that by integrating, and you end up with, you can write a similar expression here for the total flux as the integral of the local fluxes. Now, so far so good, but we still haven't got a solution. The crucial step here is to look at the situation where the drops are well separated. And in that situation, you can do it asymptotically, or you can do it in a rather more ad hoc way. But if you then analyze the limit where the drops are well separated, you end up not with the expressions that I had before, but you end up crucially with a set of algebraic equations for the total fluxes. So that may not seem like a big progress, but it is, because we've gone from the full partial differential equation problem to what is now just a system of linear equations, linear for the unknowns Fn. The F's here are the total flux. So this equation here in the middle of that slide, that's a set of for n drops, it's a set of n algebraic equations for the n fluxes, the n total fluxes from the n droplets. So that is enormously simpler to do. And that means now for a given configuration of drops, and we haven't said anything about the configuration, it can be completely arbitrary. What we now have to do is just for it, if we had 20 drops, all we have to know is where they are, and then we have a 20 by 20 system of linear equations to solve for the fluxes, which may be slightly messy to do, but is in principle always possible. And so we've turned the problem from one that was kind of impossibly difficult into something that's just a matter of solving some linear equations. And that's what it says there. So n drops, n linear equations. Once you've got the F, you can work out the J, and that's the expression then for the distribution of the flux across the drop. And I'm going to show you some examples of that. Okay, so I'm going to just show you how it works for a pair of drops. That's obviously the natural one to think about first. Two drops, identical drops, and we're going to position them so their centers are a distance b apart. And obviously the drops can't be overlapping, and so if the radius of each drop is a, the centers have to be at least 2a apart. You can go through the general theory I just showed you. It's much easier because there's only two drops, and by symmetry they're going to have the same total flux, and so you get this rather nice simple formula for the total flux. Again, if you look at the term in the denominator, the 1 plus, if it was just a 1 in the denominator, that would be the flux from a single drop. The 1 plus, the plus, is the effect of the shielding that, of course, because it's in the denominator, is reducing the total flux from each drop. Once you've got the F, you can get the J, and the best thing, I mean, that formula perhaps doesn't tell you a great deal, but you can see what it is by plotting it. Before I do that, let me just show you that the assumption that the drops are well spaced actually turns out not to really be a restriction at all. So you might imagine that assisting the drops were well spaced would mean it would only be interested in drops that were widely far apart. And formally, asymptotically, that's true. But when you compare the solution I've just shown you with a numerical solution of the full problem without that approximation for a flat drop, what you find is essentially the asymptotic solution is almost as good as the exact expression right up to the point where the drops are touching. So the top picture here actually has two curves in it. The solid curve is the numerical solution, the dashed curve is the asymptotic one, and it's really difficult to see they're different. The bottom curve is the difference between the two curves, and what you need to know here is that they're not exactly the same, but the numbers on the axis there are tiny, right? We are talking a fraction of a percent. And so even though formally this is for widely spaced drops, in practice you can use them for any configuration that you like. So here is a comparison between the numerical solution and the asymptotic one, numerical at the top, asymptotic at the bottom. And what that shows you is, at a quick glance, the pictures are identical, quite identical. If we take cross sections, then what you can see, again, there is a small difference between the numerical and the asymptotic, but in practice that difference is so small that it's really almost never worth worrying about. And this is for a situation, I think in this case, where B was 2.2, in other words, where the drops really were rather close together. And of course, the further apart the drops get, the better the agreement gets. So this is actually already a case where the agreement shouldn't be very good. And as you can see from the plot, it is in fact very good. So I take no credit for this. This is mathematics, but the math turns out to be that the agreement is very good, even for drops right up to the limit where they're touching. Okay, so now we've solved.
Stephen, 40 minutes.
Great, thank you very much. That's excellent.
Okay.
Good stuff. Thank you very much. So I'll probably talk for another 5 or 10 minutes. So, of course, once we have the evaporation problem, we can go ahead and solve for the evolution of the drop. I'm not going to try and do the details here, but I'll just show you that can be done. So, of course, again, we have an evolution equation for the volume in terms of the evaporation from each drop, as we saw before. And so, for example, the situation of the pair of identical drops, you get the equation here at the bottom of this slide. So you then have to make an assumption about the mode, just as we were talking about earlier. So if you're in the constant radius mode, you could integrate the equation up rather nicely, and you get the formula at the bottom. That's the effect of that's the lifetime of the constant radius drop. The TCR infinity is the lifetime of a drop on its own. The bracket 1 plus, the 1 is the drop lifetime on its own, and the plus is the effect of the shielding. So that shows really neatly how the effect of the shielding is to always increase the lifetime. It's the same for the constant angle mode. The details are a bit different, but the idea is the same, and the same for the stick slide mode. Again, the details are a little bit different, but the idea is exactly the same. The effect of the shielding, the effect of the second drop is slowing the evaporation of the first, and vice versa. If you plot all that information together on one slide, this is lifetime as a function of separation. You can see that as the drops get wider apart, the effect of the shielding is reduced. In the limit of a very wide spacing, you get back to the lifetime of a single drop. And what it shows you, in fact, is that when you push the drops very close together, you can increase the lifetime of the drop by, I think, up to a third for a pair of droplets. So it can be a significant effect when the drops are close together. Okay, how does this match up with experiments? Well, fortunately, there were some experiments came out in 2019 from the group from Khellil et al., who had done the experiment with 7 drops arranged in a kind of capital I pattern. And so what you've got here are the solid lines are taken from their experimental pictures. The dashed lines are the footprints of the drops taken from the corresponding calculation from our theory at different times. Of course, the agreement isn't perfect. The experiment don't perfectly similar, and our theory doesn't exactly predict the same as the experiment, but generally speaking, it works extremely well. And if you compare, for example, the diameter of the middle drop or its contact angle, you see very, very good agreement. And what I should emphasize is there is no fitting of parameters here. So what we did was we simply took the experimental values from the literature and from their experimental results and used the computations from our theory without trying to do any matching. So the fact that you can get such good agreement with no fitting is an extremely good sign and suggests that the theory is going to be a useful one. If you gave yourself the freedom to tweak the parameter values a little bit, and to be honest, values like the diffusion coefficient of the vapor in the atmosphere are a little bit uncertain, and so you would be legitimately allowed to do that. You could make the agreement even better, but we deliberately chose not to do so. So this is a quick, fast-moving field, and since we did this work, in fact, in the last month, 2 more papers from other groups have come out that I want to mention because the field's already on. So the one is the group, a paper by Edwards et al. From Nottingham Trent University in Great Britain, and what they did is they took our model and they compared its predictions for a whole variety of configurations, not just the one I showed you. They did a whole variety of things involving triangles, crosses, squares and hexagons of up to 25 droplets, and they found the same very good agreement between the two. And so they've done a very careful job of comparison. And the bottom line is that the model works really well, even for large numbers of drops and even for relatively large contact angles, which is pleasing but slightly surprising. Even more recent, in fact, almost simultaneously, a paper from Masood et al. From Princeton University and collaborators did a similar analysis, but with one very important generalization, that they looked at the same setup, but they did not assume that the drops were thin. And so by taking a kind of conceptually similar approach, but not relying on those earlier results of Fabricant, they came up with a more general version of theory that works for drops of any contact angle. and they do a very nice job in that paper of showing how well that works in the whole variety of situations. So these are both great papers, and I think they're both going to become highly cited and be the basis for a lot of subsequent work. Okay, so I can do part 3 relatively quickly, because what I'm going to do in part 3 is use the same model but turn it to a slightly different application, which is what happens to the deposition of particles. So if you take the model I've just described to you, but you account for the fact that there are particles, solid particles carried with the flow, then we're interested in how they deposit. As the picture here taken from the paper by Pritchard and Alexander shows, for a single drop, that contact line deposit will be uniformly distributed around the contact line. But for 2 droplets, you can kind of guess, I think, if you were listening to what I was saying earlier, because as the droplets come together, the evaporation is reduced by the effect of shielding. That's going to reduce the flow, and that therefore reduces the deposit. So the experimental in this are indicated in this cartoon here, that they noticed there was less deposition where the drops were closer together, and the challenge was, can that be predicted from the mathematical model? Well, I guess the answer is yes. So I've said all this to you already about the coffee stain problem, which is what I've just been describing to you. So I'm not going to try and do the details of the calculation, but basically what you can do is you can work out what's going on within these drops. We know about the evaporation, and so now we can calculate the flow. We are assuming that they're thin. What you end up with is solving an appropriate advection diffusion. In this case, you're not including diffusion. We're just looking at the advection of particles, and you can calculate where, given the particles start out uniformly distributed, you can work out where they end up. Okay, so we can do that, and the details are in the paper. That's the 2-drop problem. That's the thing I've just shown you, but what we've added onto it now with the dashed lines, these are the streamlines of the flow. So these show how the particles are moved outwards towards the contact line. And crucially, the deposit, so this is the thickness of the final deposit as you move around the circumference of the drop. Phi is 0 is the place where the drops are closest together, and that corresponds to the smallest deposit. Phi is pi, the drops are furthest apart, that corresponds to the largest deposit. So qualitatively that agrees with the experiments. These are the experimental pictures from the paper by Pradhan and Pranagani showing what I've just been describing. And so can we get the numbers to match up? Well, yes, we can. So the comparison here is between the predictions of the theory, and the jagged lines are the measurements from the experiments. And again, I just emphasize that there's no fitting of parameters here. So we have used the experimental values, the literature values of the parameters, and compared it with the predictions of the theory. And again, I think the fact that they work out so well, I mean, I take no personal credit for that. That's maths for you. I mean, it's the physics is well described by the mathematics. But again, it shows that this is, I think, is a useful way, and it's going to be a model that we can apply in other situations. Of course, we don't just have to look at 2 drops. We can look at many more. So here, for example, is what happens with 3. And here's the corresponding plot about the deposit. Again, the deposit's reduced when the drops get closer together. But what the point of this picture is just to show that it's not necessarily monotonic. And if you look at the detail of what's going on very close to where the drops are closest together, you'll see that that curve isn't just a U-shaped curve anymore. It does actually go up again in the middle. And so the thinnest deposit isn't exactly at the point of closest approach. Okay, finally, and I'm conscious that time is against me a little bit, I just want briefly to talk a little bit about what happens when you put a droplet into a well. So the situation, and this is an important problem in manufacturing. In fact, we were brought this problem by a company because they were using this technique. They were filling wells in the manufacture of OLED displays, you know, in fancy television displays. And the way they make that is they have a solid backplate into which they inject various materials in order to put the right pigments in, it will give them the right optical properties. So there's lots going on there, but the bottom line is they're filling a well with a liquid and evaporating it, and so they want to know how they wanted to know how the effect of the shape changed the picture. So we took a rather general shape, and the best way to do that is to understand that is to look at this picture here. So the top picture is a drop evaporating on a flat substrate, the problem we've been talking about before, and then the remaining pictures are for different shapes of the well. There are ones. There's a parabolic one. There's a one that's a cone-like one, and then the bottom right there's a cuboidal one, a cylindrical well. Actually, the bottom right one is the one that is closest to what happens in real life in the experiment. So, to cut a long story short, in view of the time, the drop evaporates much like it did before, but the difference here is that it may, when the drop becomes flat, it hasn't all out. Where the drop to substrate depends on the shape of the substrate. And so you can have situations where the drop dries out first at the edge and then retreats inwards in a sort of constant contact angle mode. But you can also have a situation like the one shown in the bottom right, where the drop touches down first in the middle and then dries, if you like, from the inside out. And in that case, you haven't got just a normal single drop. What you've got is a drop with a hole in the middle of it. So you can have both regular and annular drops, and which you get depends on the drop evaporating, but also crucially on the shape of the well. So it's a more complicated story, but you can use the same approach to analyze it. So I'm not going to try and do all the details, there isn't time, but just to say that the shape of the droplet is crucial. We have to solve for what's going on in the atmosphere, which we can do. We need to work out the flux, which we can do. Again, the flux is largest at the contact lines, as you find with a single drop. You can calculate droplet lifetimes. It's a little bit more complicated, but the same ideas work. And in particular, you can work out when the drop becomes flat, when it touches down, and when it all finally evaporates. And these are things you can calculate from the model. So our collaborators in Durham did experiments, and so we're able to, these are, for example, the free surfaces of a droplet in a well as it evaporates, how the volume changes as time evolves, how the inner radius evolves, it appears, and then it opens out as the droplet dries. You can compare the predictions for these things between theory and experiment. The agreement isn't perfect, but it's less than 10%. And again, this is without doing any fitting of parameter values. And in particular, this ratio of times that I showed on the previous slide, which has the advantage of not depending on so many of the physical parameters, turns out to be a very good agreement. Okay, so I just about managed it all in time. So let me just finish with some conclusions. Hopefully I've convinced you that evaporation of sessile drops is a fascinating problem, and despite everything that's been done, there's a great deal more still to do. That what are, I believe, relatively simple mathematical models capturing relatively simple physical principles give surprisingly good agreement with experiments, which is encouraging and means these are models that are worth spending time analyzing. And finally, I would say, from my point of view, none of this really would have been possible without interacting with good experimentalists. And from my point of view, the best science, the best mathematics comes from interaction between mathematicians and physical scientists who have direct access to the real world, if you like. And finally, I promised you some references. So this is a selection of some of the more recent work. And basically everything I've said, the details, all the details I wasn't able to give you in time today can be found in these papers. And so if any of that has interest to you, been of interest to you, I would love it for you if you were able to spend a bit of time looking at those papers, because I believe that there's some interesting stuff in there. But thank you very much for your attention. I've thrown a lot at you. Hopefully some of that has been of interest. And so I'm going to conclude. And if there is any time left, I'll be delighted to take any questions. Thank you very much.
Thank you very much for your talk. We have 2 questions in the chat. Pablo, you want to read it, or you want I read it?
I can ask.
Dali.
Thank you, Dr. Wilson. It's a very interesting talk. I have 2 short questions. I think when you talk about the theta star, the critical angle where the behavior changes from a pinning to a pinning stage, are you thinking about the dewetting contact angle from the? I work in that kind of problem with contact angle hysteresis. So I am thinking that this angle is the wetting one?
Yes, so it's the retreat contact angle. So it's, yes, the angle at which, so there's obviously a range of contact angles at which the contact line can remain pinned. But as you know better than I do, there's going to be a point where that no longer is possible. And when the angle gets small enough, when it reaches the critical angle, the contact line is going to depin and start to retreat. So indeed, it's the depinning, the retreating, the critical angle that you talk about. I think determining that, you can tell me, please tell me more, but for me this is a very difficult thing to calculate in general, and so in terms of our comparisons and we would just regard that as an experimental parameter. But of course there's a whole other story about determining what that angle is and how it depends on the physical properties of the liquid and the substrate, which of course in itself is a fascinating problem.
Oh yeah, thanks. And the other short question, what happened when you are comparing the evaporation of two droplets in the outside? Because you say that, of course, the presence of another drop affects the evaporation of the first one, but if you are in the, I'm thinking in agrochemical applications, what happened in the outside? And thank you, Gavin, about the talk.
Sure, absolutely. So as I say, there are many different aspects of this problem, and they're all worth studying. So everything I said today was crucially dependent on the evaporation being controlled by diffusion. So that's the simplest, I would argue that's the simplest you could do, and it seems to be relevant in a lot of situations. And certainly in laboratory experiments, they usually are very careful to ensure that it is diffusion, and they go out of their way to make sure there are no air currents or anything else going on. However, in real life, of course, that's not going to happen in general. And of course, in real life, if you're drying something, when you want to dry your washing, you put it on the washing line on a windy day, right? And the wind is absolutely crucial. So airflow above the drops, removing vapor, is crucial. And in a lot of industrial contexts, it's absolutely the dominant mechanism. And so in that case, as a principle, there's no reason why you can't take the same approach. But of course, you won't now just be plastic. You'll have to take that advection effect as well, and there's obviously been quite a bit of work on that, but it does make a lot of the theoretical approaches much more complicated. Of course, all of these problems can be tackled numerically as well, and indeed I haven't, not able to mention all of the previous work here, but there's been some really nice previous work, particularly, for example, by the group in Twente, where they've done a lot of very nice numerical work encapsulating a lot of those ideas, and indeed in some situations it can make an enormous difference. Yes, that's an important qualification that I probably didn't stress enough, that everything I've said today is definitely in this diffusive regime, and that may in practice not always be the case.
Thank you very much.
Thank you. Sebastián Noval has a question. If la leo yo si querés, Sebastián, que es cortita. In terms of time scales, is the retraction in the stick slip mode much shorter than the evaporation?
The answer is it depends. So there are definitely situations in which the amount of time it spends in the pin, the stick, is comparable to the amount of time it spends in the slide phase. I mean, what Jutta Stauber did as part of her PhD was she assembled quite a body of results from previous experimental studies, and she had a large selection of examples where that was the case. However, it's not always the case. And there certainly are situations where the slide phase is much faster than the stick phase. And that, of course, in the limit, gets you to that stick jump mode. The stick jump mode, it's basically stuck all the time, apart from these very rapid jumps. So you can have, there's a whole continuum of behavior from roughly kind of 50-50 sort of, roughly equal amounts of time in both modes. And it's certainly absolutely possible that those slide or jump events can be very rapid. And it depends on the fluid, the substrate, the situation, and so both scenarios are definitely possible and definitely worth studying.
Okay, thank you. Javier Diaz, you can.
Thank you, Mario. Yes, I really enjoy your talk, Stephen. Really very nice and very clear. So I have I think I have many things to comment because you went through so many subjects. But one thing I was seeing is that, or that I have seen in the literature, if there are several proposals for the flux from the drop, from the evaporative flux. So it seems that for your scheme, you only have one fixed type of evaporating flux that looks like a very simple formula as you showed, J sub 0. But I've seen in the literature that there are others which have a lot of parameters which are not so simple to deal with. So how do you compare these results with other formulas, and why there are other formulas which are not very similar to yours?
Well, I mean, you're absolutely right. So it's a long, fairly complicated question about what actually an evaporation. You know, there's a lot of work on evaporation of liquid into its sphere, and of course, in general, it's so what we have here, what the model I've described, is very much the simplest version of that, and the simplest possible version is that results in a saturated atmosphere and then a constant concentration. However, of course, if you look in the physics, the thermodynamics books, you'll find that can be generalized in a kind of arbitrary large number of ways. You know, in general, things depend on the partial pressure, and the partial pressure can depend on a whole variety of different circumstances. So what you can certainly find in the literature are more general evaporative laws, depending perhaps on temperature, pressure, and various other things that seem to be important in the different experiments. I think it's true to say that at least most of those models reduce to something like what I've got here in the appropriate limit. I think that the proof of the pudding, to a large extent, is does it all match up with experiments? And I think the reason this model is not, I mean, the model could be just so laughably simple that it's not worth studying. But the fact is, there's a wide variety of physical situations where to capture. However, absolutely important to say that it's not the definitive model in all cases, and there are certainly situations, more extreme situations, where this simple model ain't going to work, and you're going to have a more sophisticated model. I would say there is also a body of work on kind of non-equilibrium evaporation, where the evaporation is actually not controlled by what's going on in the atmosphere at all. It's all controlled by what's going on in the drop. Now that's certainly, there are situations in which that's true, and there's a large body of work doing that, because theoretically it's very
yes, because you're not solving at all the flux inside the drop. You just solve the Laplacian problem for the.
That's right. So I am, yes. But there is another body of work based on everything being based on the drop side of things, if you like. I mean, the truth is that these are all special cases of a much more general configuration, and which is the right model to use depends on the situation. What I would say is there is definitely a large region of parameter space in which this simple diffusion model works, but it is definitely not the whole story. So there's more to do.
Okay, and within your scheme, you have these regimes, contact, where the radius of the drop is decreasing or it remains constant. And what comes out from your modeling for the radius as a function of time when it is decreasing? Or because there are a lot of laws like Tanner's law, Cox-Boynoff law that relates the radius of the drop and the contact angle even without evaporation. Now you have evaporation, so I think that you can get also a relation between the contact time velocity and contact angle. And are there in the limit of evaporation going to zero, go to Cox-Boynoff model or Tanner model? I haven't seen that. So
no, that's a good question. I mean, you won't get a kind of Tanner law because there's no detailed information about what's going on near the contact line. What you get from this is a relationship between the expression and for the volume, and the volume is a combination of the radius and the angle. So in any one case, if you make an appropriate assumptions, you can solve. So for example, if you assume the radius is constant, you can solve for the angle. It's a simple formula. If you keep the angle the same, you get the radius coming out. Or if you do these mixed modes, once you've made your assumption, you can follow through and work out the answer in any particular case. But the model as I've presented to you lacks a crucial extra bit of information, and that information is the detail near the contact line. So this doesn't replace the need to do that modeling. What it's done is it's really kind of sidestepped it by just replacing that with an assumption. You could, an interesting problem, which we haven't done, but would be interesting to do, is to use something more sophisticated like a Tanner law or Cox-Boynoff law and build that in and ask what effect that has on the overall dynamics. I mean, that would be another assumption, but it would be a very interesting one.
Okay, yes, thank you. Thank you very much.
No, really good, interesting question, though. Thank you.
Thank you. Okay, we have a last question from Pablo Keller, who says, would it be possible to include within the model a solute whose concentration that would increase as the evaporation evolves and whose concentration modifies the diffusion properties?
Absolutely. So as I think what I've described here in terms of the dynamics is very much the basic model, and there's a whole variety of ways you can generalize this. There's been quite a lot of work on effects of surfactants and surface active and soluble materials. There's a whole question about how that affects what's going on in the drop. There's a large body of work on how the presence of a surfactant affects the surface tension. There's a lot of work on Marangoni flows. There's also the issue of how the temperature affects everything, because really, the temperature, you can get quite big temperature changes. As the drop evaporates, it cools. I didn't talk much about that, a little bit. Of course, the fact that the temperature is not constant means density, surface tension, you name it, all diffusion coefficients in principle are all functions of temperature. And so if you're in a situation where that matters, you've got to put in all the extra complications. So certainly, absolutely, there's definitely you can build some of these things in. And there has been already quite a lot of work in many of those directions already. So yeah, it's a problem that just keeps on giving. And depending on your interest and application and a particular problem, there's a whole variety of ways of building on some of the things I've talked about here today. I think we'll probably keep us busy for a little while yet.
Okay, thank you very much. I guess that other question could be done by mail if you don't bother.
Absolutely, yeah. Please feel free.
Okay, thank you very much. And very clear your exposition. And no, thank you. Thank you.
And thank you again very much. And thanks to the audience for their patience. Thank you very much.
Yes.